Hello and welcome to Implementing Flux Minor. In this section, we'll build a data store using a design based on the Flux pattern, which we'll call Flux Minor. We'll begin by building a store that contains our application state and has the ability to make updates to it. We'll then spend 2 lessons learning how to bind our data store to the view layer using subscriptions. We'll close with a reflection on the design decisions we made, like immutability and functional programming, as well as some of the limits of our design. Today's lesson focuses on using a data store. In our previous video, we saw how to use React context to make data implicitly available further down in the component hierarchy. Today we'll be building a centralized data store that's capable of storing and updating the state of our entire application. We'll begin with a quick overview of the Flux pattern itself. We'll then build out the logic for managing the state. This starts by defining a set of possible state mutations, which we'll refer to as actions. Then we'll write a bit of code that applies those mutations to the application state. We'll also be testing our code along the way using Jest. Now before we start coding, let's review quickly what Flux is at a very high level. These diagrams are basically it in a nutshell. We don't need to fully understand what these pieces do right now, but we should keep this picture in our heads as we're learning the parts. The gist of it is this. The store contains the data that gets displayed by the view. A user interaction sends an action to the dispatcher. The action describes a state mutation, and the dispatcher sends this to the store, which uses the mutation to update itself. The view layer is then notified and can update itself with the changes. For today, we can pretend that the view doesn't exist. We'll be building out a lightweight version of everything else, where simple actions do most of the work. So we'll begin with those. Let's imagine that we're building a simple counter application, and our application state is an object with a single member variable n. So we need to define actions to describe what sorts of mutations are possible to this state. One easy way to do this is with a function that takes the current state and returns a new state. So for example, an increment action would be a function that accepts a state argument and returns a copy of the state with n incremented by 1. Notice an important point here that we'll keep coming back to. The incoming state variable isn't modified itself. We're returning a copy instead. An action by itself should just be a description of the mutation that's taking place and should not create side effects by making changes to the input. Let's define a decrement action in the same fashion. We're now ready to write our first tests. We want to make sure that our actions do what they say they do, so we'll import them both and test them against some input. The first test will ensure that increment will add 1 to our n variable. So if we define our state object with n equal to 0, we should be able to feed that to the increment function, and the n that comes out of it should be larger by 1. I can make a nearly identical test for the decrement action. At this point, we can run our tests. Create React app comes with Jest built in, and running the yarn test command will run Jest in watch mode so that our tests will be executed whenever we make code changes. The output reveals that all of our tests are passing, so we can be confident that our actions work like they expect. But actions by themselves don't do anything. According to this diagram, we still need a store and a dispatcher to tie this stuff together. So let's create those next. To create a store, we'll define a function called createStore that accepts the initial state of our application. We can then save the initial state as our current state and then expose a function called getState that returns the current state. This is still fairly uninteresting, but let's test this getState function before we move on. Now we'll use the describe block to set up a few tests against our data store. First, we'll import the createStore function. And now we'll define an initialize function that will return a new store with an initial state where n is set to 0. Now we can write a test against our getState function to make sure that it returns the initial state. So back to the output, all of our tests have rerun and we see that everything is passing. So we're actually really close to being done. We just need to define the dispatcher, which is actually going to be exposed from the store itself. So this will just be a function called dispatch that accepts an action as its only argument. We then expose the function from the store object that we're returning. We're now ready to test this one. So we'll write tests that dispatch actions against the store and verify that the internal state has changed. Let's do increment first. We initialize the store, dispatch the action, and make sure that n has increased by calling getState to check the state of the store. We then do the same thing for the decrement action. All of our tests are passing, so our store must be working like we expect. That's all the time that we have for this lesson. Today we learned how to implement a data store using Flux Miner, a flow-based data store that's based on Flux.